Okay, I think that we are ready. Once again, thank you for joining us today at the HSE University's online Master of Data Science degree programs industry webinar. And let me introduce the speaker, Denis Rakitin, who will tell you more today about the neural program synthesis. And before we will start, I'd like to mention a few organizational moments. So first of all, we will share the recording of that webinar after I think in 2 or 3 days. So you will receive the email with the information with the recording. And also one more moment I'd like to mention, if you have any questions during the presentation, you can type them in the Q&A box. So there is also a chat box, but please type your questions in Q&A because it will be easier for us to track all your questions and answer to them. So, and if you have any questions regarding the program and admission, you can type also them on the Q&A, and I will provide you detailed information. But today our webinar is not about the admission. So yeah, Denis, for you.
Yeah, hello everyone, and thanks for participation. Okay, I started sharing the presentation. Can you see it? Yeah, okay, great. So today we will talk about so-called neural program synthesis. This is a contemporary approach for solving program learning problem. And this problem contains of automatically generating a computer program, which is consistent with some specification. So it could sound like something difficult or maybe not, but we will first start with observing some examples of it before we proceed. So speaking a little bit about the overview of the talk. First of all, as I said, we will give some introduction about what is program learning with some examples. And after this, we will try to talk about how can we actually combine the approach of program learning with the approach with neural networks. So if we talk about the combination of two approaches, this can be done actually in two directions. The first direction is to apply a neural network for solving the program learning problem. And the second one is to try to use some intuition, to use some algorithms or maybe some structures from program learning when considering some classical neural network task. So the first type of combination about applying neural networks for solving some program learning task will be about the string editing. And this domain is actually is actually known for all of us, and we'll observe it like just on the next slide. And the second type of combination using program learning for neural networks will be considering visual question answering. That is, if you have like an image and the paired with a question about some objects in this image, you want to give an answer to this question. So this is just an outline of what we will discuss today, and starting with the examples. So the first example, as I announced, is the example of string editing domain. And the simplest version of this is like looks as follows. So I believe you all you all used Microsoft Excel spreadsheets, and I believe you are used to the situation where you have a column with some string entries, and you want to process all of those entries in the same way. So just like this, imagine that you have a column of 12 names of months of the year, January, February, March, etc. And you want to like produce the shortened version of those names. So for January, this is Jan, for February, this is Feb, for March, this is Mar, and you want to the output string to be in the lowercase. But from the user's perspective, like, okay, if we can actually process this manually, so we can look at the input column and we can just type all of the 12 shortened names at the right, like at the output column. But imagine if we have a column not of 12 entries, but of thousands of entries. Then we have I believe two possible directions. First of all, is to spend a whole day just typing those transformations manually. The second could be actually to write some program that will make this transformation for you. But there is some problem. First of all, we want to, from user's perspective, we want to do as less as we can. And not all of the users of, for example, Microsoft Excel are programmers. So making some program which will give you the desired transformation could be difficult. And I believe any of us doesn't want to spend the whole day just typing those transformations. That's why we can actually try to give some black box at this moment algorithm the numbers of input, a few number of input and output string, because any user, despite here being a programmer or not being a programmer, he can just make a few number of those transformations manually. For example, as like this, we have just the user just needs to type 3 strings, Jan, Feb, and Mar. And then we can put those pairs of input and output examples into some algorithm, which will produce us the program that will make the transfer that is able to make those transformations correctly. And this is exactly as it works in Microsoft Excel. So here, for example, all we need to do is just we can take a look at this string. We can we need to take the substring from the first character to the third character, and then we need to process this substring to make this lowercase. And this is actually what is written. Well, and this actually corresponds to the program that is written here. And I've written spec at the right just to, okay, I said that program learning is about constructing a program consistent with some specification, spec for specification. And here the specification is just a few number of input and output examples of the evaluation of this program. So, okay, I believe this is quite a practical motivation because so okay, because we talked about the pain of the user when he needs to process a huge number of strings and to transform them in like some way. But this is not all. A little bit more exotic example is about graphics generation. So if any of you if any of you used LaTeX, and in particular here some graphics from TIX module of LaTeX is represented. This is actually a picture that was taken from some paper. And imagine that you need to, okay, maybe you make some report about some project and you need to make some plots, some graphs, some charts maybe. And if you try to make this in LaTeX, this is this is a lot of pain, because you need to really to spend half an hour or maybe an hour to just draw some like very simple types of images. What could be actually do, and what is and what was the attempt of authors of the paper from which I took this image, is just to try to design an algorithm which will be able to process the like hand printed images. So I believe this is so okay, this is quite easy to like take a pen, take a list, take a piece of paper, and to just draw to make a plot that you want to add to your report. After this, we just like take a photo of this of your handwritten plot, put this into some algorithm. In this case, this is an algorithm which is combined with the neural network. And we get the program in LaTeX that will generate us that will generate us the graph, the plot, which will reconstruct what we wanted quite good. So this will make some approximation of what we've drawn. This is also a practical type of question because it could potentially save a lot of time. Okay, and moving on to the next slide, we can also observe a lot of more examples. So, but the example at the left, I believe this is not so practical. It's more about some funny example or just an example which is interesting to research. So at the left, you can see an instance of Carol robots programming language, which consists of all possible operations which will move robot, for example, at the left, at the right, which will check if there is an obstacle behind him, at the left of him, at the right of him. I believe this is an example of a programming language which can be, for example, used as a tutorial programming language for school students. Okay, so in Carol programming language, all of the instances are just we have some obstacles, we have a robot, and we want to write a program such that the robots will move from the point A to the point B, moving like so. For example, in this case, he's just inside some labyrinth and he wants to go out. So we have point A at the position of the robot and the point B where is out of this labyrinth. And yeah, we need to design some program which will lead our robots to move from point A to point B. This is actually quite interesting whether we can design some algorithm that will, for example, take the map with the position of the robot and with the position in which we want the robot to end, and to produce us some program which will lead robots move correctly. And even maybe even more interesting whether it could be done with using some neural networks. And at the right, you can see actually an example of a visual question answering problem, but I will not focus on it right now. We will talk about it a little bit later. So speaking a little bit about neural networks themselves, I believe, so even if you are not really familiar with them, this is not a great problem today, but some like classical maybe definitions or like intuition about it is given at this slide. So neural networks are usually used for modeling data, which is okay, I named it like X, but X can be anything. X can be an image. X can be like text, a text, and etc. Or so, for example, if we have the data set of images of dogs, we could want to like make a neural network that will produce us new pictures of dogs. This is about modeling data X, but we also could want to model some data dependencies between X and Y. For example, the most typical example is where X is some image and Y is some class of this image. So, for example, if we have two classes, we could potentially want to classify the image that we get. But Y can be also anything. For example, X can be the text. So some text, for example, written in English, and Y can be some the translation of this text written in Russian. So X and Y could be defined depending on the particular problem. But this is about the nature of neural networks. They're about modeling some data or some dependencies in data. But formally, neural net. So how can we model those type of dependencies? We see like the arrow from X to Y, and this mathematically leads to some functional dependencies. So formally, neural network is some function that takes X, so image, text, or something else, as an input and produces outputs Y. This could be, for example, the probabilities of this picture being a dog or being a bread, as in the example at the right. This can be also like a text, the translated text. But this function also has the second parameter, and not just one parameter, but usually millions of parameters. Those are here denoted by W, and those are the set of all weights or parameters of the neural network. And actually, when we talk about training the neural network, training is all about searching such type of parameters that the resulting function with those fixed parameters will capture the data dependencies quite well. Here is some like a non-formal thing about what do we mean by saying that it captures the dependencies well. It can be formalized with loss functions, for example, if you know about it. And so this is more about the training process. Today we will not talk a lot about training process, but we will make some a little bit of comments about it. And yeah, usually neural networks are trained on a set of pairs xi and yi. So for example, xi is an image and yi is the ground truth, so-called class of this image. This is just an example. It can be like a set of pairs of English and Russian sentences, which are translations of one another. And quite an important thing that contemporary neural network tends to require more and more data to train on some hard problems. And if we try to consider larger neural networks, that is, neural networks with a larger number of possible parameters to make predictions in some more like sophisticated domains, they tend to require more and more data. And this can be actually some problem because data is not limitless, and we need to somehow search for this data. But I believe that's more or less all about this slide for neural networks. So moving forward, I would like to talk about some motivation behind combining neural networks or using neural networks for program learning tasks. So imagine we have a little bit number of input and output pairs, and we want to predict the transformation of the input string into the output string. Or we want to, for example, make a robot move from the point A to the point B, as we observed in the first examples. So first motivation is that, okay, I believe I didn't fully write the first statement, but so we all know that people are able to derive concepts and extract some regularities from data, even from a small amount of data. So if you take a look, for example, at the transformation from January to Jan, you easily like generalize it to all possible examples of names of months. Yeah, even talking about this. Even talking about this example with generating program consisted with some input and output examples, it hardly resembles the machine learning task actually, because in machine learning we have a set of pairs of input and output examples, and we want to learn some transformation between input domain and output domain. So it could be interesting whether neural networks are able to solve this type of problem. Moving back to to the observation that people can learn and can generalize even from a small amount of data. This task, generating a computer program consistent with specification, can be actually seen as potentially potential benchmark for artificial intelligence. I'm sorry, as potential benchmark for artificial intelligence. So the statement could be like this: if the some algorithm, very general algorithm, can solve for general input and outputs, can produce the program which will be consistent with them, then this algorithm is actually an artificial intelligence. This motivation is more about some research or maybe some philosophy, but not about some practice. But can we achieve some also practical benefits? We'll see. But first of all, what we need also to talk about is that, okay, I believe that when someone hears that we use neural networks to write code, so like quite a usual question could be, okay, so right now we don't do we actually need programmers if we can just use neural networks for writing some code? And I formulated this in this slide, like, are neural networks Python coders? But actually no, because all of the practical programming languages that are that we use, actually they are too hard, because they are a really huge number of different functions. They have quite difficult semantics, so they have quite difficult structures in them. And these today's neural networks are not actually able to capture all of these structural dependencies, all of those, to remember all of those functions. This is just a really hard task. But okay, if we want to use neural networks for solving program learning tasks, we want a neural network to generate a program. In what programming language do we want to generate a program? If we do not, if we cannot use some usual programming languages as Python, C, C++, etc. So the answer here is the domain-specific language. The domain-specific language, so it follows from its name actually. The domain-specific language is some number of is a language which is designed specifically to the task that you are trying to solve. So imagine that you want to build some you want to build some okay, you can imagine just a simple calculator as a programming language. It will just consist of 4 possible operations: of plus, of minus, of product, and of division, which all of those operations take a pair as its input. So plus of AB is equal to A plus B, etc. After this, we only need, so we just fixed the all possible operations in our programming language, and after this, all we need to do is just to fix some semantics. So we need to fix which programs are correct and which are incorrect. And this is pretty much all about this particular instance, because yeah, we do not have to use Python or C or C++ to solve this like very simple task. We can just use 4 operations, and learning those operations will be actually possible for neural networks. And moving forward to string editing algorithms. So the ultimate tool which is implemented in Microsoft Excel, it is called flash-fill algorithm. It has no neural network. It has a really sophisticated domain-specific language with a huge number of operations, and the work process of this algorithm is also pretty hard. It's so imagine you have quite a hard programming language. It can have billions of possible programs, or maybe like practical programming languages have infinitely many possible programs, and we somehow need to search for a single program which will be consistent with our input-output examples. Or maybe not a single program, but just at least one program that will be consistent with our input-output examples. And so this algorithm is this algorithm uses a lot of smart search techniques in the space of possible programs. It uses some branching, some division of the space into subparts, and it actually finds the programs pretty fast. But this approach required really a lot of engineering. So this is not straightforward to realize such type of algorithm to generate programs. But instead, moving back to our motivation about our observation that the program learning task quite resembles the task of machine learning, we can try to use neural networks. So the algorithm, which is called robust fill, which introduced, I believe, 2 years ago, maybe a little bit less than 2 years ago. This is an algorithm which is built built on the neural network. It also has to define some domain-specific language. It also has to define the programming language in which we want to generate a program. But here, the programming language is much easier than in Flash fill. Okay, and the scheme of the work of this algorithm is actually pretty easy. So we have some so-called labeled pairs, inputs paired with outputs. So those are pairs that the user made manually, and after really few number, for example, 3 input examples, and the user wrote 3 output examples that are that corresponds to those 3 inputs. And after this, we have a lot more number of inputs. So those inputs that are processed by user, so inputs paired with outputs, are put into the neural network, which after this generates some computer program. And this computer program, we can just execute it. So all of the new inputs, which can be like hundreds or thousands, we can just process all of them by this program. So we generated a program that we believe is consistent with the input and output examples. And if we put new input examples into this program, we believe that it should work and it should process new outputs carefully. So this is like a whole idea about this algorithm, but the difficulties here are so the only formal things and mathematical things that that are actually here is like, okay, first is the design of the domain-specific language. Second is the design of the architecture of neural network, and the third is the design of training procedure. But we will omit this to because this is this could take really a lot of time, and this is a little bit about more topic. So, okay, we built this type of algorithm. We have a neural network which predicts a program, and after that, we execute the program on new inputs that we want to process. But okay, we just had the classical algorithm, which is called Flash fill, which is implemented in Microsoft Excel, which works invisibly fast, which is pretty good. But why could we actually try to solve the solved task with another approach? So do we achieve any benefits from this? But actually, yes. So take a look at the examples from the left. We have some strings containing names, surnames, and we want to process them in the following way. We want that the output string will firstly start with the surname with a comma with white space, and after this it should have a name which should also start from the capital letter. But what if we take a look at the example from the left? It actually contains some errors, because if we want to process John Smith in this way, we would obtain Smith John, not Smith Jin. So this is a mistake. And if you take a look at the third line, you can see that Frank Lee, with some numbers, with some additional characters that we do not care about, is processed as Lee Frank, but the second letter is capital, which we do not want to, we do not want it to be. Yeah. So what could what will be, and so the question is following: what will be the performance of the flash fill algorithm implemented in Microsoft Excel, and what will be the performance of the neural network approach if we try to use them on like those noisy inputs, or if we try to use them on inputs which contain errors. So you can take you can take a look at the plots at the right. So the violet line is about Microsoft Excel's flash fill, and all other 4 lines are about some different architectures of neural networks. So some of them are more powerful, some of them are less powerful, but you can see a trend. The trend is that if we have like 0 noise characters, if all of the characters in input and output pairs of strings, which are processed by user, which are given by user to generate a program, if they do not have any errors, then the flash fill algorithm produces the best results. But 2 of the architectures of neural networks could actually process, could actually achieve the competitive results with flash fill. But the trend is as follows: when we start to increase the number of noisy characters, flash fill algorithm starts to work pretty bad. So even if you have 1 noisy character, the accuracy is below 30%. So we just like the more frequent situation in this case is that we have an incorrect program then we have a correct program. And as for neural networks, their accuracy fall down by like 2 or 3% per noise character. And even if we have 10 noise characters in the output string, in input or output strings, both, we actually are possible to get a program which will be correct, like in 60% of case. But when we have 10 noisy characters, I believe this is quite a great result. So what we actually got when we moved from the existing approach to using neural networks, we get that our new algorithm is more robust to noise than the previous algorithm. Previous algorithm had some really smart techniques, but it's false. It's okay. We see that it is quite unstable to noise, but neural networks are have quite a probabilistic nature. So, for example, in image classification task, instead of just outputting the number of class, so outputting a cat or dog, we output probabilities of the image of being a cat and of being a dog. And this follows for, I believe, pretty much all of the domains where neural networks are used. So they have a probabilistic nature. And if we add some noisy characters, I believe, so the noise is actually an example of some probabilities is also an object of a probabilistic nature. Actually, this nature led us to the algorithm, which is quite robust to those types of bugs. And those types of bugs are pretty relevant in practice, because the input and output strings are processed by user, and we are all people, and we all can make mistakes. So as we see, starting from some motivation, which was like about some research or about some philosophy, we actually got an algorithm which has some practical benefits. Okay, this is more or less all about the application of neural networks for solving program learning tasks. And moving on, we will observe some, so second part will be about building a program learning block as a part of a neural network architecture. But first of all, what if we try to combine a neural network with not just, not in particular the program learning block, but any like structure block, which is designed to capture the dependencies on data, to capture some prior knowledge about it. So here is the example that I really like a lot. it was taken it was taken from one of the recent papers about making those type of structures for neural networks. So imagine if imagine that you have a task of so imagine you have a data set of reviews of beer, text reviews of beer paired with the ratings of aspects of beer. So here, as you see, it is appearance, aroma, plate, taste, overall, from 0 to 5. And imagine that you want to predict the grade that some person puts to this beer by the text of his review. So so it could be seen as quite an interesting task. But imagine that you want to actually do something more tricky. Imagine that you want not just to predict predict the grades that a person did, but you want also to predict to outline the keywords that could be used to motivate why the prediction, our prediction with some neural algorithm is correct. So what are the benefits of this type of problem statement? So first of all, if we state a problem like this, we can learn some additional information from data, because in machine learning, the most common scenario is when we train our neural network or our different machine learning algorithm on pairs of X and Y's, on pairs of input and in pairs of inputs, objects and outputs. But here, if we have a data set of texts paired with the grades, we do not have actually those keywords. But we could potentially try to learn those keywords actually without knowing them without actually knowing ground truth keywords. So we could try to learn some additional information from data that is not explicitly presented in the data set. But the second potential benefit of providing our neural algorithm with some structure block is that we could potentially achieve better results by knowing structure of data, because we wire prior knowledge about data in our neural model, and we could actually expect that this could make the quality better. But okay, if we consider in particular the program learning block, what could we get? So I see there is some question, but wait a second, please. I see that there is some question, but I'm not capable of opening it. Sorry.
Maybe I can help you. There is a question in the Q&A. So are we assuming that these texts are unlabeled, if I'm mistaken?
Okay, thank you. So in this example, we assume that we want to predict the grade by looking at the text. So we have a label. We actually have a labeled data set. We have a data set of texts X and paired with grades Y. But we can actually reproduce, while the learning procedure, we could incorporate some so-called latent variable Z, which will represent this subset of keywords. And there are actually some algorithms that are capable of learning with those latent variables, and they are called latent because they are not present in the dataset explicitly. So did I answer your question? So I do not know how to see whether I answered your question or not. Okay, this is great. So if we consider in particular a program learning block, what could we get from this? First of all, neural networks are quite hard to interpret. And this is actually quite this is actually quite an important thing when we talk about, for example, decision making with the high responsibility. We want to be we want to be confident in the predictions of our neural network. And if we want to be confident in the predictions of our neural network, we want this neural network to be interpretable. So we should know what are the we should know how the neural network makes the prediction. And if we incorporate a program learning block into the neural network, it makes the interpretability much easier, because this is much simpler to look at the program that a neural network generates instead of learning on millions of parameters of neural network. Well, okay, we can actually try to test our neural network making predictions on some inputs, on some transformation of inputs, and try to make some and try to obtain some knowledge about the now our neural network. But okay, this is also can be really hard in practice. So programs could introduce something interpretable into our neural network. This is great. Second observation follows the observation from the previous slide about about the observation that the structural knowledge can increase the quality of our prediction. But the problem with all of those types with this type of algorithms is that it actually needs some additional design of training algorithm, because introducing some first of all, programs have discrete nature. Discrete nature can be quite hard to mix with some gradients and etc. So we need to carefully think about the design of training algorithm. But okay, we do not have a lot of time, but I will try to be a little bit faster. So speaking about visual question answering, we can actually so for example, try to look at the picture, look at the question, and answer this question. I believe people like processing those types of tasks. First thing that they do is we first build the representation of the image in our mind. And then we look at the question, and for example, here we have, are there an equal number of large things and metal spheres? So first of all, we need to make a capture to capture this image. Then we need to process all of the possible objects of from this image. We want to calculate first the number of large things, and here they are 1, 2, 3. We next want to find all metal spheres, and here they are 1, 2, 3, 1, 2, and 3. So what we actually do, we I'm sorry, VQA stands for visual question answering. So about this type of task, and neural symbolic VQA is the name of the paper which introduced some neural algorithm to solve this type of task, from which I took this example and the overall scheme. Yeah, so we first make some scene representation in our head, and after this we make some very algorithmic processing of it in our head, which leads to some idea that what if we have first of all some neural network which makes a readable representation of the scene from image. We call this network a scene parser, and okay, if we try to, if we look at the question and we repeat the process of answering this question, this quite resembles the some algorithm. So we need to first of all filter all large things. We next need to filter all metal spheres. We need to count the number of filtered things in first one, in the second one, and then to compare them, and then to answer some question. This leads to an idea that the questions can be actually represented as programs. So we then we will have some additional neural network that will read a question and output some program that will, combined with the scene representation, give us an answer to this question. This is the main idea. This is the main scheme. Here, there are a lot of questions about how to train this type of thing, but we omitted a little bit. And speaking about the algorithm a little bit more precisely, first of all, we have some neural networks. So authors used so-called mask RCNN, but whatever. We have some neural network that looks at the image and extracts all of the relevant objects from this image. So here we have 5 objects, 1, 2, 3, 4, 5. Then we have an additional neural net, which processes those objects and produces the table which corresponds to the scene representation. So we have a table of in which all possible objects from this image are listed with some some of their qualities, like the position at the scene, shape, material, and color. After this, we have a question: how many cubes there are behind the cylinder are large, and this represents, and we have a neural net that produces the program, which we will use to solve this question. So we have 5 consequence operations in this program: filter, shape, scene, cylinder. So this is pretty logical because we want to see how many cubes are behind the. So we want to take a look at the cubes that are behind the cylinder. First of all, we want to filter all the cylinders from the scene. Then we want to look at all of the objects that are behind this. So we have some sub scene. We have a sub list of objects from the image. Then we just need to filter cubes from them. Then we need to filter large cubes from them and just count. And this is what is represented in this program. After this, we just process the input, which is structural scene representation, with the received with the program that we got by the neural network, and we get actually the answer. So this is the whole pipeline of this algorithm. And what are the benefits of such an implementation? First of all, in this paper on which from which I took this algorithm, the results are pretty close to 100%. What is even more interesting that they used only less than 300 of programs to train a program generator. This is actually this is actually really a little number of examples. So I said that neural networks tend to require larger and larger number of examples, but here the number of examples is not so great. But authors trained this neural network not with ground truth programs that are able to generate those type the programs that we need by looking at the questions, but they also continued training on pairs of image and question with answer pairs. So and they also used quite a small amount of those type of pairs. I believe it's okay, it's less than 10,000, and it is also considered as quite a small data set. And this all was possible only because we know authors know how to generate the data in this data set. So okay, this is quite this is a little this resembles a little bit a toy example because the objects on the scene are pretty easy. They have not a lot of attributes such as shape, material, color, and we actually know everything about the generation process of this data. That's why this is not really a practical algorithm. But this algorithm shows that providing our neural algorithm with some structural knowledge about data could result in an algorithm that is really data efficient and which is really accurate. So this is the second benefit that we can get if we combine program learning with the neural networks. Okay, what can be done next? So algorithms that were represented in the string edited domain and in this visual question answering domain, they were actually trained on generated programs. But imagine in practice that you want to solve some visual question answering task on like just some photo. It is hard to imagine that you will be able to generate a data set of ground truth programs that will that will be wired with some ground truth questions. So this is quite an impractical direction. Yeah, so like this is what I wrote here. Such data set is really hard to generate in practice, but actually the authors of the paper of the paper about visual question answering produced some after this produced some new algorithm which gets rid at least of this training with the ground truth programs. So this step could be potentially overcome. But okay, there so a whole lot of questions about these types of neural algorithms, about those types of machine learning models are about some training, and yeah, this is like quite a recent research sphere, and it is quite interesting whether we can somehow make those type of algorithms really really useful in practical tasks, considering something like visual question answering or something or just some task which is solved by the neural network. But at least we can see that combining two approaches can result in quite an efficient algorithm, and this leads some motivation to investigate those types of combinations. And as for conclusion, so we observed using neural networks for program learning, and we've seen that it can be actually beneficial. We achieved some robustness to noise, which we did not have. Can we see the code of which algo? So yeah, I actually realized, yeah, okay. I actually realized that I did not place the links to the corresponding papers at the presentation, but if the presentation will be at Coursera, I will modify it a little bit and add links to all of the papers from which I took those algorithms. So not all of them have like the code on GitHub or somewhere else. So and the code will consist of a huge number of lines. So this is something quite hard because it needs to train a neural network to process inputs with neural networks after training, and the algorithms are quite unusual here. So if it is interesting for you to see the details, so I would like then I will ask to help me with the adding some links to Coursera where this recording will be, and I will also add these links into the presentation. So we observed that the first algorithm which was called robust fill about string editing, the application of neural networks here can be beneficial in, for example, robustness to noise. If we consider the opposite direction of combination about program learning for neural networks is the potential in interpretability and the potential in data efficiency. Okay, but this type of approach is quite hard to design in practice, but it is promising because it addresses the practical problems and it achieves some results that we quite desire to look at in practice. So I believe this is quite all. Thanks a lot for participating. And I believe here starts the question and answering session. Yeah, thank you. I'm glad to hear this type of feedback from you.
As I see, there are no questions. So in that case, Denis, thank you once again so much. And I'd like to thank all participants for joining us. In case of any questions regarding our online program, you can email us and I will post the email address on the chat. And we'll be happy to provide you the detailed information. Thank you.
Yeah, I see. I'm sorry. I see one question, and maybe I did not state it quite explicitly, but all of these algorithms are not like some of my inventions or some of inventions of my colleagues. This is just some paper from. So the paper is like some scientific paper. I mean, from which I read because I was interested in it, and so like this is not my invention, but maybe I did not say something about it quite explicitly. So those are the algorithms that were developed by some research groups. First, I remember from Microsoft, and second about visual question answering, I do not quite remember, but yeah, something like this.
Yeah, thank you. Thank you. Have a good day. Have a good evening. Thanks for joining us. Bye.
Yeah, thanks. Bye.